All right, we are all done with the world of mechanics, and we are now going to be going into some different areas of physics, starting with waves. So there are different categories of waves. There are what are called mechanical waves. Mechanical waves require a medium to travel through. Now, when we say a medium, we're talking about an actual material. So examples of mechanical waves are things like waves in a spring, sound waves, seismic waves, that sort of thing. Electromagnetic waves, that's a different category. Those types of waves do not require a medium to travel through. So those are the types of waves that can travel through space then, which is good for us because that's the kind of radiation that we get from the sun that warms up our planet and allows for life to exist here. Electromagnetic waves all have the same velocity. There's different types of electromagnetic waves. You guys have probably seen the electromagnetic spectrum before. Starts out with radio waves having the lowest amount of energy. Then there's microwaves and infrared, and then there's the visible light spectrum, which goes from red through violet. Then there's ultraviolet, X-rays, gamma rays. So all of those types of electromagnetic radiation travel at the same speed, which is the 3 times 10 to the 8th meters per second. We call it the speed of light because light was the first type of electromagnetic radiation that humans knew of, because that is the part of the electromagnetic spectrum that stimulates the retinas of our eyes and allows us to see things. So we call it the speed of light, but it's really the speed of all electromagnetic radiation. 3 times 10 to the 8th meters per second. One of those numbers that you should get to know, much like gravity being 10 meters per second squared. Now, within those categories of waves, there are different types of waves. There's a transverse wave. Transverse waves, that's probably what you typically think of when you think of waves. That is where the particles of the medium move perpendicular to the wave motion, or to the wave direction. We actually should rephrase this. They're moving perpendicular to the energy. What a wave is a transfer of energy. Okay, a longitudinal wave, that's where the particles of the medium move parallel to the energy. So once again, we'll change that to energy. And then with a surface wave, what kind of happens is the particles will move both perpendicular and parallel. So they go kind of around in a circle, and surface waves are also called rolling waves because they go around in a circle. A wave pulse, that's just a single disturbance, a single amount of energy traveling all at once. Traveling waves are produced by sources that vibrate with simple harmonic motion. Like if we tied a string to the mass on the spring that bounces up and down, the string would send wave after wave, and so we would have a traveling wave. So kind of a representation of all those things. For a transverse wave, if this is the equilibrium or rest position of the medium, as the energy travels in this direction, the particles of the medium are going to vibrate up and down. And so we get this kind of pattern. Transverse. The particles are vibrating up and down, perpendicular to the motion of the energy, which is going in that direction. For a longitudinal wave, what happens is as the energy travels in that direction, the particles of the medium vibrate back and forth in that same plane, and what we end up getting are areas where the particles of the medium are bunched up closer together than they normally would be, and areas where the particles are spread farther apart than they normally would be. Okay, you get the idea. So these areas where the particles are bunched up or compressed together more than they normally would be, those are called compressions. And then these other areas where the particles are spread out farther apart than they normally would be are called rarefactions. All right, with a surface wave, as the energy is traveling this way, the particles of the medium go up as they move outward, and then back down as they vibrate horizontally backward. So they're traveling up and down and back and forth all at the same time, and it gets them to go around in a circle, like a wheel or a ball would. And so surface waves are also called rolling waves. These are the types of waves that you get on the surface of a body of water. That's why if you ever like sit on a raft in a wave pool or something, you could feel yourself going up and down and back and forth all at once. Or if you're ever on a big ship out in the middle of the ocean, you might be able to feel that. Wave pulse. Again, would be a single disturbance in the medium, a single pulse of energy, you might say. Again, a wave is just energy being transferred through a medium, or in the case of electromagnetic radiation, not through a medium, but through space. And then a traveling wave would be, again, let's say you got something here that's vibrating up and down, and there's a string attached to it. As that thing vibrates up and down, there's going to be waves created by it in this string, one right after the other. So instead of a single wave pulse, you get a bunch of wave pulses, and it looks like a traveling wave. Okay, a little bit of math to go along with this stuff. Some properties that waves have. Waves have a period, which again is just like the rotational motion stuff. It's the time required for one wave to pass a fixed point. Or in other words, the time required for one complete cycle. Waves also have a frequency, which is the number of waves that pass a point in a second. So if you look at those two things, period would be the seconds per wave, and frequency would be waves per second. And so those two are inverses of each other. So period can be calculated by taking 1 divided by the frequency. Frequency can be calculated by taking 1 divided by the period. The wavelength is the distance between two identical points of a wave. And that is how far a wave travels in one period. And so that's what we use to calculate the speed of a wave. So if we look at your typical transverse wave, this is our equilibrium position or rest position for the medium. There's our transverse wave. A wavelength can be calculated or measured between two, these are called crests. Yeah, I think we get into those on the next slide. So yeah, we'll just go ahead and worry about that picture in a little bit. So a crest is the highest point of a wave, the highest point that it has above the equilibrium position. A trough is the lowest point below the equilibrium position. Amplitude is the maximum displacement of the medium above or below. So it's basically the crest or the trough. And then the more energy that's being transferred, the greater the amplitude is. All right, so let's try that picture again. There's our equilibrium position. Here's our transverse wave. There's two consecutive crests, and we measure the distance between those two, and we've got the wavelength, which is represented by that Greek letter lambda. We could also measure the wavelength between two troughs. We could measure it between this spot where the particles of the medium start to vibrate below equilibrium and the next spot where the particles start to vibrate below equilibrium. You get the idea. Two identical points on a wave. So again, these up here are crests. This is a trough. The measurement from equilibrium to the top of the crest or equilibrium to the bottom of the trough is the amplitude. All right, so wave speed. How fast are these waves moving? You guys would have learned in earth science that P waves travel faster than S waves. There are different types of waves, so they cover more distance in the same amount of time. Or, in other words, that can relate to their wavelengths and their periods. So since we know that V is equal to D over T, when we're talking about waves, we can measure the distance that a wave travels in one period, which is an amount of time. That distance is called the wavelength. And of course, that time again is the period. So for wave speed, speed is the wavelength divided by the period. So it's still a distance divided by a time, just very specific distances and times that we're talking about. And since a frequency is 1 over the period, dividing by the period is the same as multiplying by a frequency. So most of the time, this is how we represent wave speed, lambda f, the wavelength times the frequency for a wave. So an example problem might look like this. A hiker shouts toward a vertical cliff. Let's see what it is. A hiker shouts toward a vertical cliff that is 685 meters away. The echo is heard 4 seconds later. So first of all, we want to know what is the speed of this sound wave. So when this hiker shouts, he produces a sound wave. That sound wave travels through the air, hits the cliff wall 685 meters away, bounces off, or some of it bounces off, and comes back to him, and that's what he hears 4 seconds later. Now, this is a classic type of problem, and which, easiest thing to do is to draw a picture of what's going on. So here's our cliff wall, and our hiker is standing over here. Maybe try to put a little backpack on him, because, he's hiking. And when he shouts, the sound wave is going to travel to the wall, bounce off the wall, and come back. And is heard 4 seconds later. So this is a distance of 685 meters and a total time of 4 seconds. So the time for the sound wave to travel to the wall and back is 4 seconds. We want to know how fast the sound wave is going. Now, we don't have any information about frequency or wavelength or anything like that. So we've got to use our old V equals D over T equation to find out the speed of the sound in air. Now, they gave us a distance, they gave us a time. Pretty simple, right? Not quite. If you take a good look at it, the sound wave travels the 685 meters to the cliff wall and then travels 685 meters back to the person in that 4 seconds. So we can do one of two things. We either double the distance that they tell us, because the sound wave technically travels to the wall and back, or we can cut the time in half, because if it takes 4 seconds to get to the wall and back to the hiker, then it's going to take half of that time, 2 seconds, to get to the wall. That's what I'm going to choose to do. So time is 2 seconds to get to the wall. .685 meters away. So I'm going to use that distance of 685 meters and the time that it would take to get from the hiker to the wall, which would only be 2 of those 4 seconds, to calculate the speed of the sound in air. So 685 divided by 2, 342.5 meters per second. Then it wants to know, if the wavelength is 0.75 meters, what is the frequency? So if the wavelength is 0.75 meters, what is the frequency? Well, we know that speed for a wave can be found by taking wavelength, which is that, times frequency, which is what we're looking for. So, to get the frequency by itself, we simply divide both sides by the wavelength. So our frequency is equal to the speed, which we found in letter A, divided by the wavelength, which they just told us in letter B. So 342.5 divided by the 0.75 meters. And that comes out to 450, I'm just going to round it off to 457. Now, we take meters per second and divide it by meters. Technically, the seconds is down here on the bottom because we're dividing by it. And the meters is going to cancel out. So 1 over seconds, what they did was they named that after a scientist who did a lot of work in this field. And the unit for frequency is called hertz, Hz. So hertz, spelled just like the rental car company, and abbreviated Hz. So the frequency of the sound is 457 hertz. And lastly, letter C wants to know, what is the period? Well, we know that period is seconds per wave, while frequency is waves per second. So to get the period, we just have to take the inverse of the frequency. So 1 over 457 hertz would be 0.002 seconds. All right, that's pretty much all there is to it. Waves, it's pretty easy. So hopefully this helps. We'll see you tomorrow.